Let's talk about type annotation. I'm not going to go crazy into depth with type annotation, as that's something I cover in my course and it would be way too much to fit inside of a single video, but I will show you how to get started with type annotation. Before we start talking about type annotation, we should discuss the difference between dynamically typed and statically typed languages. Lua is a dynamically typed language, meaning that the values stored in variables can change during runtime. Like if you had a variable storing a string, during runtime you could change that value to be something like a number instead. That's a dynamically typed language. A statically typed language means that values in variables are created during compilation and they cannot be changed during runtime. This means you would have to declare the type of a variable in a statically typed language, like declare a variable is going to be storing an integer or a boolean or a float and so on. In Lua, type annotation allows us to declare the type for a particular variable, a parameter for a function, or the return value from a function. The cool thing about this is that it helps us improve the readability of our code, and it also assists the linter in Studio to give us some autofill features, which can make development faster. For example, let's say we had a function called sum. We want to get the sum of two numbers, let's say a and b. If we were to go and call this sum function, obviously we would likely think that a and b has to be some kind of number, but unfortunately, autofilled here it just says a is a and b is b, and that's because we haven't type annotated anything. It doesn't really know what a or b is, and if we accidentally pass, let's say, a string or a boolean or some other value that isn't a number, it's going to cause errors inside of the function. So wouldn't it be neat if we could have the ability to check what value is being passed to A or B, and if it's not the expected value, we can send out a warning into the console, and also when we go and type out a function, it should autofill and tell us what exactly these different parameters are supposed to be, and that's what we can use type annotation for. Now for this video, I'm going to be setting the type inferencing mode in this script to strict, and I do so by making a comment with an exclamation mark and saying strict. Now, a type inferencing mode defines how the type checker for Lua should infer the types of variables. If we set it to something like no check, then this will not check types. It's basically going to ignore types. If we set it to non-strict, this is supposed to be the default mode, and it's only going to assert the type of something if they are annotated by us in the code. And then if we set it to strict, what it's going to do is it's going to assert all of the types of specific things based on the inferred type or the annotated type. So when I mean inferred, if my sum function returned a number, but I don't define it using a type, it's going to infer that the type returned from our sum function is a number. So that's going to be the strict mode. Now, I don't believe that non-strict is enabled by default yet. Let me go to beta features and see if it's still a beta feature. Okay, there we go. So scripts are non-strict by default. Script analysis uses non-strict mode for all scripts by default. This is still a beta feature, so they haven't enabled this by default yet. If you want your scripts to be non-strict by default, then you would enable this beta feature and save it. But we're just going to leave it off for now. And I'm going to set the type inferencing mode for this script to strict. So this should be your comment at the top of your script. Now what you're going to notice is that when I call the sum function, as you can see now, it has inferred that it's going to return a number because I declared a number right here. So it says, hey, this function returns a number. Now for me to declare the type of these two parameters, a and b, I need to put in a colon, and then I need to type out what type we expect for this particular parameter. Now I expect a number, so I can just type in number, and as you can see, it autofills right there. And then I can also declare the type for b to be a number as well. So now if we were to write out our sum function, as you can see, it now says it takes a number for a, it takes a number for b, and it returns a number. This is type annotation. So what I can do here is I can return a plus b, and then it's going to infer that our sum function still returns a number, and that's because we're just returning a and b added together, and since a and b are both numbers, it's obviously going to infer that it returns a number. If we want to explicitly say what type a function returns, then we can put a colon after the ending parentheses and then type out what type it returns, like a number. If we need a function to return more than a single value, So let's say it returns multiple different values, right? The way we can define that is by putting a parenthesis here, and then putting another parenthesis here, and then using a comma to separate the other type it returns. So let's say for some reason our function returns two different numbers. As you can see, there we go. We type annotated that. Now, if you notice, we're getting a little bit of an error here because it says expected to return two values, but we're returning only one. That's the strict inferencing mode and the linter letting us know, hey, you made a mistake here because you're supposed to be returning two different numbers, but you're only returning one number. So to satisfy that, I'll just return a plus b twice. And there we go, that error is now gone. Now down here, we're also getting another error, and it says argument count mismatch. Function sum expects two arguments, but none are specified. We've called this function, but we haven't passed any values to A or B, and it's letting us know, hey, you forgot to pass some values here. So I'll be like, oops, sorry. Let me fill that in, and there we go. That error is now gone. Now let's go ahead and take a look at something else called a union type. A union type basically means that a particular variable or parameter can be more than one type. So it could be one type or another type, or it could be this type. Pick one out of a list. So the way we can define a union type is by using the vertical bar symbol. So for A, maybe we could pass both a number or we could pass a string. You can basically think of this vertical bar as an or statement or something like that. So now if we were to go and call our sum function, you're going to see that A can be passed a number or it can be passed a string. This is a union type. And of course, we can continue adding vertical bars to say that this can be passed either of these different types. And we're not restricted to only the data types that are native to Lua. We can also use other data types. For example, let's say we can get past a humanoid to a function. So this could be passed a number, a string, or it could be passed a humanoid. And because we've declared the type of this parameter be a number, a string, or a humanoid, it's going to autofill with those different features depending on how we refine the type of A. What do I mean by refine? Well, we need to help out the Lua interpreter determine what the actual type of A is, because it could be a number, it could be a string, or it could be a humanoid. How do we check? Well, we can check using if statements. For example, if I were to check the type of A, and we're going to say A is equal to the type of number, then that means inside of our if statement block right here, A is going to be inferred or refined to know that it is a number because we checked right here. If the type of A is number, then we know that A in this particular block of code is a number. But if we were to check the type of A and found out that it's actually a string, then in this particular refined block, we know that A is a string. Now, something very cool about type annotation is, let's say A is going to be a humanoid. So we expect the type of humanoid. Because we expect the type of humanoid, that means A is now automatically inferred to be a humanoid, and we're going to have access to all of the different properties that a human has, like its diet event, its ancestry change event. We can check its health, we can set the jump property, and all this different stuff. So just by type annotating it, we were able to autofill it with all of the different properties for humanoids. If we didn't do that, and let's say we expect A to be a humanoid, but we didn't type annotate it as a humanoid, as you can see, when I use my dot operator, I'm not autofilling anything. So that means I have to manually type out the properties by hand, which can be slow and annoying. So if I know that the input to a function, let's say A has to be a humanoid, then I can type annotate it and then get all of the different properties. And now I can use tab to autofill this stuff, and it is much faster than me having to manually type it out. Now, you might also know the Variadic symbol for functions. So if we put 3 dots, that means this function expects a variable or an unknown amount of arguments, and we are actually able to declare the type for these unknown arguments. So if I want my sum function to take an unlimited amount of numbers, then I can define the type for this variable amount of arguments to be of the type number. So now if I were to call my sum function, as you can see, it tells us it takes an unlimited amount of arguments and they all have to be of the type number. Another type I want to show you is something called a singleton or a literal type, which means that we basically declare the type of a parameter or a variable or whatever to be a literal value. Currently, this is only supported for strings and booleans. So let's say my A parameter here has to be the string of hello. This is the literal type that A has to be. So if I were to call my sum function, it's going to tell us that A has to be hello. And if I were to put parentheses here, as you can see, it's autofilling, telling us all of the different options we can have for A. And since A has to be hello, the only option right here is hello, and we can autofill that. But maybe we can pass multiple different strings, like hello, we could pass hi, and then we could pass maybe howdy. So now we're basically combining a literal type and a union type together. So now if I were to put in my parentheses, as you can see, I have 3 different options that I can autofill into my sum function. I can put hello, hi, or howdy. And this can be very useful if you want to create your own custom enums or things to that nature. Type annotation is very useful for that. Now, all the stuff you've been seeing me doing for parameters also works with variables. So if I created some variable here, I can also use a colon and declare the type of this particular variable. For example, I can declare it to be the type of a humanoid, and now when I refer to some var, it's going to have all of the properties of the humanoid autofilled, even though I haven't initialized some var with any kind of value. We can also use union types and say maybe it could be a humanoid, or maybe it could be a C-frame or something, I don't know. We can also use literal types. We can say that some var has to be a string of hello, so some var is a string of hello. And now let's say I declare the type of some var to be hello, but then let's say I set it to the value of false. We're going to run into an issue here because the type boolean of false could not be converted into our string type of hello. So this is how you type annotate for variables. You simply put your colon, then your type afterwards, and then after you've put your type, then you can use your equal sign and assign a value to that particular variable. We can also create our own custom types, and we can do so by using the type keyword, and then we can use or create a name for our type. So I'll just call this my example type, and we can set it equal to some kind of value. For this example, I'll set it equal to a table, and inside of this table, maybe it has maybe it's an array, right? So it's an array of C-frames. So we could just do something like that. So now if I were to create an array here and I were to cast it with our type of example type, if I were to refer to array, it says that it's an example type. And then if I were to loop through different objects inside of this array, so for every single object inside of my array, my object is automatically going to be inferred as a C-frame because that's what I've declared this type to be for my example type. It already knows what object is. We could also define that maybe our example type has a key of like hello, and the value for this key, we're going to put a colon here. Maybe it has to be a string, and then it also has another key like howdy. This has to be a number, and then maybe it has a third key like hi, and it has to be maybe a boolean. So now if I were to create a variable and cast it with my example type, and then I were to index it, as you can see, it's going to show those different keys, and it's also going to show what value is stored in those keys, all through type annotation. Now, since we can create our own types using tables, we can add types together and create something called an intersection type. So I'll show you an example of that. Let's say I have a type, let's call this xcord, and it's just going to be a table with a key of x, and it has to store a number. And then let's say I have a type of ycord. This is a table with a key of y, and this has to be a number as well. And then let's say I have a type of zcord, and this has to be a table with a key of z, and this is also a number. Now, wouldn't it be cool if I could combine these 3 types into a single type? So basically, I have a table with an x, y, and z coordinate, or maybe I have a table with only an x and a y coordinate. Well, this is where we can use intersection types. I can create a new type here. For example, I could imitate vector3. So I'll just call this vect3, and this is going to be equal to my xcord type. And then we use the and symbol to join multiple types together. And then we can join it with the y coordinate, and then we'll use another and symbol and join it with the z coordinate. And now if I created a variable like, I'll just say hello, annotate it with the type of vect3, 3, so my custom type right there. If I were to index hello, as you can see, we have access to the x, y, and z variables, and they're all annotated as numbers. And that's because we have joined these separate types together into an intersection type. So these are intersection types. They only work with tables. Okay, so the next thing you might be wondering, how do we type annotate something to be a function? So let's say we had a variable like a, and let's say a was actually a function. How can we type annotate a to be a function that takes some kind of input and gives an output? Well, I'll show you. We can type annotate functions by using a pair of parentheses followed by a dash and then using the right-hand caret. So you'll basically form an arrow. The font that I'm using creates this little arrow symbol when I do that. And then we have to pass another set of parentheses. And now we have type annotated a to be a function that takes no input and gives no output. So if I were to refer to a and then I were to autofill it, as you can see, it's automatically going to put in those parentheses to basically call a because the type checker thinks a is a function. This is how we type annotate with functions. Now, if I want to define parameters for my function of a, then I can do that. So I can define that a takes an input of x, which has to be a number, and an input of y that has to be a number. And then we could say a returns a number and it returns a string. I don't know. So now when I go and refer to a, as you can see, it has now autofilled a to be a function that takes an x input and a y input of numbers, and it returns a number and it returns a string. Pretty cool. Now, something you have to note when you're type annotating something as a function like this is that if your function takes a variadic number of inputs, you might think to type annotate it like this, but this actually isn't going to work. We're going to get a problem right here. It says expected type got colon. And to actually type annotate in this format with variadic types, you just put your 3 dots, and then after your 3 dots, you just put the type. So now if I were to autofill a, as you can see, it says it is a function that takes a variadic number of arguments, and those have to be numbers. So this is how you type annotate in this format. And then when you're actually type annotating within the parameter section of a function, it's okay to create your 3 dots and then put your colon and declare the type that way. Just a little difference between doing it these two ways. Okay, another thing I want to talk about here is something called type casting, and that's when we explicitly cast a type over some kind of variable or parameter or something when the inferred type is too generic, basically. So you'll see what I mean in a second. I'm just going to change up my sum function to take no input, and it's just going to return, let's say, a base part, right? So I'll create my variable, I'll call it a, and it's going to get the return value for my sum function, and that means my a here is a base part. Now, sometimes that might be a little bit too generic. What kind of base part are we talking about here? Is it a part? Is it a wedge? Is it a mesh? Or, you know, what is it, right? Well, if sometimes if the type is too generic and we can cast a type over it, we can do so like this. We can put 2 colons, and then after these 2 colons, we can define a type. And let's say we want to do a mesh part. So now a is going to be inferred, or basically have the type casted over it, of mesh part. And this works because base part is the base class for all parts in the game, including mesh parts. So we were able to refine it a little bit more by giving a more specific type, and we've casted that over our variable of a. Another example of type casting I'll give here is, let's say we had a table called my table, and let's say inside of this table we have a key, I don't know, I'll just call it values, right? And we want to be able to, actually let me set it equal to a table, and then let's say we want to be able to define what this table has to store. Maybe it has to be an array of strings. Well, you might think, okay, I'll just put a colon here and then just say this is a thing that takes strings, but then you're going to notice, wait a second, we're getting a whole bunch of issues here. How am I going to be able to define the type of this values key to be an array of, string? Well, we can use type casting. So we can put 2 colons afterwards and say that our values key right here has to store an array that stores strings. And as you can see, now we don't get any errors. And then if I were to refer to my table and then refer to values, as you can see, it now understands that values is an array of strings. This can also be useful when we need to resolve some errors. So for example, let me redo my sum function here. Let's say it takes A, and let's say it takes B, and this function returns a number. And now let's say A is a number, and now let's say B is an optional parameter, right? We're not required to pass B to this function. The way we denote that is by referring to the type, and then we put a question mark afterwards. And this question mark basically says B might be a number or it might be nothing. We don't know what B is going to be, so this is basically an optional parameter. Now the issue with this is that if we return A plus B, we're obviously going to run into some problems here, and it's because it says type number question mark could not be converted into number. So because B could possibly be nil, we basically can't do this operation here. Now a way you could think of fixing this would be to check if B doesn't exist. So if we do not have a value in B, then we can set B to be some kind of default value like 1. But then the problem with this is that if we go take a look here, we're still running into an issue of type number question mark cannot be converted into a number. We're still having this problem. So a way we could fix this is basically cast the type of number over B here, or basically over this return value. So if I put 2 colons here and then say this has to be a number because we've just verified up here in case B doesn't exist, we set a default value, then we can be like, hey, B is a number, and there we go, that error has now disappeared. This is a little bit of an iffy thing with type annotation. Even though we put a check up here to make sure that B is actually a number, we still get this problem here because the type checker isn't that smart, so we have to explicitly cast the type of number over B to get rid of that particular problem in our code. All right, I know I'm all over the place right now, but there's just so much to talk about with type annotation. And the last thing I want to go over with you with type annotation is something called generics. So let's go ahead and take a look at that. If I were to create some kind of custom type, let's say I call it pair, and let's say I set it equal to a table that has 2 keys. So let's say it has key 1, which has to be, let's say, a number, and it has key 2, which also has to be a number. Now the problem with this pair type is that it basically only accepts numbers for the first key and the second key. What if we wanted the ability to create multiple different pairs based on multiple different types? Like instead of a pair of numbers, what if we wanted to have a pair of strings, or a pair of C-frames, or a pair of humanoids, whatever? We want the ability to basically create something called a generic where we can define what the type is going to be ourselves, but still has basically this type annotation or this type declared for us. So if I were to create a variable called A and cast it with the type of pair, as you can see, when we refer to pair, it's obviously going to have key 1 and key 2 that are numbers. But what if we want key 1 and key 2 to be strings? So what we can do instead is make pair a generic. And the way we do that is by using an open char and then a closed char, or a less than and greater than symbol. And then inside of that symbol, we create a placeholder name to represent a type. We can make the name whatever we want, but most of the time you'll see it as an uppercase T. And now we've created this generic with this some kind of generic type here. And then we can cast, or basically type annotate key 1 to be of this unknown type T, and same thing with key number 2. So now what we do here is that when we annotate A to be pair, or B of the type pair, we can then define the type. Let's say we want it to be a string. So now when we refer to A and we get key 1, as you can see, key 1 is a string and key 2 is a string. If we want it to be a number instead, we can type annotate it to be a number. And now a.key1 is a number and a.key2 is a number. Maybe we don't want it to be a number, maybe we want it to be a C-frame. So we can pass the C-frame type. And now key 1 is going to store a C-frame and key 2 is going to be storing a C-frame. And of course, they're filled with all of the autofilled stuff for C-frames. So this is the useful thing with generics. It allows you to define a generic type, and then you can define the type that you want it to store. So this basically allows you to reuse types. And you can do the exact same thing with functions as well. You can create something called a generic function. And if you've seen my video on functional programming, you saw me use generic functions to create a generic map function. But I'll show you how we can do this. If we create a function and we were to call it something like, I'll just call it hello. before we put our 2 parentheses here, we need to go ahead and add our less than and greater than symbols. And then we can define a type here. I'll just call it T. And let's say A has to be the type of T. Now we've created a generic function. So when I go and call my function and I were to pass like a string of hello here, as you can see, it has automatically set the type of A to be of string because that is what the type is for that first parameter. And we're not restricted to only one unknown type. We can put a comma here and declare another type. We call it type K. And let's say we need to take an input of A, which is of the type T, and an input of B, which is of the type K. And then let's define a third type. We'll call it U. And let's say this function returns the type of U. So now we have created a really generic function, and this looks a little bit confusing. But as you can see, A is a string, B is going to be, we'll just put a number. So we'll do 1. And then A is going to be a return or whatever U is. Now let's actually have a little bit of fun with generics. What I'll do is I'll create a function called map, and it takes in, let's say, a type of type T and a type of type K. And basically we'll get passed an array, and this array is a table containing things of the type T. And then we'll get passed a function. We'll call this the mapping function. And it is a function that takes an input of T and it returns this type of K. Let's do something like that. And then let's say this function returns an array filled with these K variables. So this is going to be basically a standard mapping function. If you don't know what mapping functions are, I recommend for you to go and check out my video on functional programming so you can get a better idea of the application for generic functions. But basically how this works is that we'll create a table called results, and then we basically loop through all the different values inside of our array. And then inside of our result table, we basically set that exact same value at this index, but we need to pass it through our mapping function, which will return to us a different value. So we would call the mapping function and pass this value to it, and it would give us that type of K, and we store that inside of our result table. And then at the end, we return the result, which is an array of those types K, whatever K is going to be when we call this function. So now when we call the map function, we could have an array of numbers like, let's say 1, 2, and 3. And our mapping function is going to take an input. So that'll be V, we'll call it V. And V is going to be a number, and it has to return this unknown type. Currently it says it's A. But let's say it takes this value of V, which is a number, and let's say it converts it to a string. So we could do return to string V. And now if we take a look at our function here, it's going to show us that, okay, our map function takes an array input of numbers. Our mapping function takes a number input and returns a string. And finally, our mapping function or our map function returns an array of strings. And then I could print this out into the console. And then if I were to execute the code, as you can see, we're now going to have an array. Instead of storing numbers, it's going to be storing strings. So that is a mapping function. It just takes an input and maps it to the same position, but with a different output. Okay, this was basically a brief overview of type annotation. This video is probably a little bit too long, but hopefully you now have a better idea of what type annotation is and how you can use it in your games. Thank you for watching, and I will see you next time.